Dear students, I welcome you all for this the other session of my subject. In this session, we are going to discuss the application of the MFR equation. That is using the mixed flow reactor equation. So how to find the design variables? Either we may have to calculate the reactor volume or the volumetric flow rate of the stream or the space time. So how to find the design parameter for a mixed flow reactor, that we are going to see in this lecture now. So for that, so I have taken a problem here, so which comprises of a liquid phase reaction. The statement of the problem is given in a simplified format here. So the reaction is a liquid phase reaction. The stoichiometry is A plus 2B, giving us R with rate equation. So A moles of 1 mole of A is reacting with 2 moles of B to giving which will give us 1 mole of R. So this stoichiometry is having the rate equation minus R is equal to minus RB by 2 is equal to 12.5 CACP square minus 1.5 CR. So the stoichiometry is given along with the rate equation. Now this reaction is taking place in a mixed flow reactor having a volume called as 6 liters. So this reaction occurs in a mixed flow reactor with a volume of 6 liters capacity. Now, for this MFR, since two reactants are involving in the reaction, so two streams will be entering into the reactor also. So the first is called stream A, having a concentration of 2.8 moles of A per liter. The second is called as stream B. It is having a concentration of 1.6 moles of B per liter. So two streams are entering into the reactor, mixed flow reactor, and each of them are having the equal volumetric flow rate. That means stream A and stream B, they are entering into the reactor at equal volumetric flow rate. Same volumetric flow rate. So same volume per unit time. So that basis it is entering into the reactor. Now 75% conversion of limiting component is desired. So first we have to identify what is the meaning of which one is the limiting component. Then that component conversion value is given as 75%. So what we have to find is small va, small vb we have to calculate. That is nothing but volumetric flow rate of stream A and stream B. Separately we have to find it. Now this entire problem statement can be represented by means of a schematic diagram here. So this diagram is showing the mixed flow reactor. So where we can find two streams are entering. So this is the stream A, this is stream B. It is entering into the reactor. Now outside the reactor, the stream concentration is taken as CA0 dash. So that the dash represents the concentration of reactant A outside the reactor. That is given as 2.8 moles of A per liter. So that is a given data. Now CP0 dash is also a given data, that is equal to 1.6 moles of B per liter. That is outside the reactor. But when they are combining together and combinedly when they enter into the reactor, the concentration value will be decreasing, because see outside the reactor the concentration value is 2.8 moles of A per liter. So this is also like 1.6 moles of B per liter. If they are entering at equal volumetric flow rate, for the combined stream inside the reactor, the concentration will become into half of the given value, because see inside the reactor the volume of the system becomes as 2 liters, because here also we are getting 1 liter, here also we are getting 1 liter. For example, the stream A is entering at a volumetric flow rate of 2 liters per minute or 1 liter per minute. Some flow rate, just assume some value for that. Now the same volumetric flow rate will be there even for the stream B also. If that is the case, inside the reactor, the total volume becomes equal to 2 liters. For example, here we are getting 1 liter, here also we are getting 1 liter of component B. The solution volume becomes as 2 liter now. That means inside the reactor, the CA0 value is half of the concentration that is there outside the reactor. So 2.8 becomes as 1.4 moles of A per liter. See, this 2.8 moles of A, that is for 1 liter outside the reactor. But here it is for 2.8 moles of A per 2 liter. That becomes as 1.4 moles of A per liter. Like that, within the reactor, the concentration value will be reducing into half of the given value. That is what here also it is explained. Since equal volumetric flow rates are flowing into the reactor, The CA naught value now becomes as 2.8 moles of A per 2 liter. That is by 2 liter we will be having. The system volume now becomes as 2 liter. That means the actual initial concentration is taken as 1.4 moles of A per liter. Like that, for CB0 is equal to the actual initial concentration should be equal to 0.8 moles of B per liter. Now, from this two concentration, if we compare the value of this two concentration value, we observe that the CB0 value is less than CA0. That means the quantity of B is lesser than the quantity of A. So that B is the limiting reactant. That means the given conversion value, here it is mentioned that 78% conversion of limiting reactant is reserved, or it is desired value. That means that XB value to be taken as 0.75, the conversion of component B, because B is the limiting reactant. Now, for mixed flow reactor, the performance equation in terms of component B can be given as tau by CB0 is equal to XB by minus RB. This already we know what is the design equation or performance equation for the MFR. So tau by CB0 is equal to XB divided by minus RB. See, on cross multiplication, we get tau is equal to CB0 into XB divided by minus RB. Let us to call it as equation number 1. Now this value of this quantities and all we have to get separately. For example, CB0 value is known 0.8 moles of B per liter, XB value is 0.75. So only one unknown thing is minus RB. But this rate equation based on component B is given. For example, here it is given as minus RB by 2 is equal to 12.5. Expression is given here. So take this 2 to the right hand side. That means you get minus RB is equal to 25 CA CB square minus 3 into CR. That is what given here also. So that given equation is written in terms of minus RB. So for that the 2 is taken to the right hand side. So this becomes as 25, this becomes as 3. So the rate equation in terms of B is now written like that. It depends on 3 variables called as CA, CB and CR. Now if it is enough if we find the value of these 3 concentration values. For that, let us go to the next step. The CB is equal to CB0 into 1 minus XB. This equation we know, that is how to find the CB value. CB is nothing but the residual concentration or the remaining concentration of component B. See, now that is equal to CB0 into 1 minus XB. CB0 value is 0.8. XB value based on the condition, limiting reactant is component B. XB value is a given data, 78% conversion. So XB value is equal to 0.75. That means 1 minus 0.75. See, on simplifying these values, we get CB is equal to 0.2 mole per liter. Like that, CA is equal to CA0 into 1 minus XA. So multiplying this term inside, we get CA0 minus CA0 into XA. The CA0 value is known. For example, CA0 value here it is 1.4 moles of A per liter. So it's again a known value for us. How about the CA0 XA value? CA0 XA, see, it is having the meaning called as amount of A reactor. The CA0 XA is nothing but the amount of A reactor. Now, see, there is no way to find the CA0 XA directly because CA0 is known to us, but XA is not known to you. Okay, so we have to indirectly get the value of the CA0 XA. For that, we use the relation from stoichiometry. So stoichiometry says that A plus 2B giving us R. That means for every the amount of A reacted, the amount of A reacted is equal to half of the amount of B reacted. Is it right? So from stoichiometry we observe that the amount of A reacted is equal to half of the amount of B reacted. That means we can see here that for every 1 mole of A, 2 moles of B is getting consumed. So I can use the relation here. So amount of A reacted is equal to half of the amount of B reacted. So that is in terms of variable. It is written as 1 by 2 into CB0 into XB. So already we know what is the value for the CB0 XB and all. CB0 value is 0.8, XB value is 0.75. See, upon simplification of all these numerical values and all, we get the value as 0.3 moles per liter. That is the CA0 XA value. Now CA is equal to CA0 minus CA0 XA. This already we know. This value just now we got it. Substituting it here and then simplifying it, we get the value of CA. CA is equal to 1.1 mole per liter. That is the remaining concentration of component A. Now, I think we need 3 values. CA, CB value we require, CR also we require. Now we got these 2 values. The last one to be found is CR. So how to find CR value? CR is equal to, again use the stoichiometry relation. From stoichiometry we find that 1 mole of A is giving us 1 mole of R. Stoichiometry is saying that. Okay, that means amount of A reacted is equal to amount of R formed. So CR is nothing but amount of R formed. That should be equal to amount of A reacted. So that is equal to, see, amount of A reacted is nothing but CR into XA. So again already we got the CR and XA value equal to 0.3 mole per liter. So which in turn is equal to CR. So CR is equal to amount of R that is formed out of reaction. Substituting all the concentration values in that rate equation. So minus RB is equal to 25, CA value we know, CB value already we know, CR value just now we got it. Substituting all the values here and then simplifying it further, we get the minus RB as 0.2. That is the reaction rate value. Okay. Now go back to equation number 1. Actually equation number 1 we have defined here. Tau is equal to CB naught XB divided by minus RB. This is already predefined thing. Now from that let us to find what is the value of tau. Tau is called space time. So tau is equal to CB naught XB. CB naught value is 0.8, XB value is 0.75, minus RB value is 0.2. Substituting all the values in this equation and to get what is the tau value. Tau value is 3 minutes we are getting. Already we know what is the definition for tau. Tau is nothing but space time. It is the ratio between the reactor volume to that of the volumetric flow rate at the inlet condition. So V divided by V naught. Tau is nothing but V divided by V naught. So V by V naught is equal to 3. That means V naught is equal to, cross multiplying it, we get V divided by 3. So what is the value of this V? V is again a given data. V is the reactor volume that is given as 6 liters. So substitute it here, 6 liters divided by 3 minutes. So which is coming around 2 liters per minute. So this V naught is the combined stream volumetric flow rate, that is equal to 2 liters per minute. This is the total volumetric flow rate or combined volumetric flow rate of both the streams. Now for separate streams actually it is given that equal volumetric flow rate are entering. So combined stream flow rate is 2 liters per minute. So for individual stream it should be like 50 equally distributed. These two should be distributed equally for both the streams. That means 1 liter per minute for each stream. So 1 plus 1 we get 2 liters per minute as the combined volumetric flow rate. Okay, since we are following the condition of equal volumetric flow rate, so this 2 should be distributed equally for both the streams. That is why it is taken as small VA is 1, small VB is also equal to 1. 50% contribution or equal contribution by both the streams. So this quantity only we have to find for the given problem, for the given MFR. I hope this problem is clear to all of you. So if you have any clarification, you can contact me. Otherwise, I request you to go through the contents or the step-by-step procedure for the problem also. I hope the problem is very clear. If any doubts or any clarifications if you are having, you can contact me later on. So thank you for listening to my lecture.